we are back and we're going to do our problem set 1 solution videos. So I'm using an XRD, I'm measuring the last parameter A of chromium. I'm going to load my sample into an XRD, copper alpha radiation, hit sample different angles. We produced intensity versus 2 theta curve. We can use Bragg's law to calculate these interplanar distances if the material is cubic. Calibrate my apparatus with sample silicon, had to use some curve drawing software to identify peaks from the intensity. So I need to draw the generalized measurement diagram for this experimental apparatus. So let's say, I mean, it's not super clear here, but I think that we're trying to eventually calculate this value and to determine essentially those other things. So my measurand is DHKL. DHKL. So that's my measurand. It's going into stage 1, but before that stage 1, there's a calibration with sample silicon. So I need to calibrate first. If we look back at our notes, then we have our sensor transduction basically stage. So we need to detect and sense essentially the measurand. So in this, our sensor transducer is going to be, so we have, when we do an XRD, you basically shine the XRD, the X-ray is here. So there's an X-ray generator. You have a sample, it bounces off. We have our detector here. So our sensor and our transducer would probably be the detector. Detects the signals, that gets that intensity versus 2 theta, and then we're allowed to do that. Now the signal transduction phase, one of the transduction is going to be, or actually not the signal transduction, excuse me. One of the signal conditioning phases in stage 2, that is going to be a couple of things. So it's going to be this equation goes into signal transduction, this one, or signal conditioning, this one goes into signal conditioning, and also this curve smoothing software as well goes into that. And then your readout will eventually be your intensity versus 2 theta plots, and thus finally the readout of the value there. There we go. Again, don't overthink it. Just describe as best you can, add as much as you would like, and then you're good to go. Measuring the tire pressure in my tire pressure gauge. Nominal pressure is this voltmeter. Ooh, not my voltmeter. My pressure sensor measures 40 psi, but measure pressure 100 times. Fluctuations in my measurement never exceed this. Pressure target describe the voltmeter's accuracy, resolution, sensitivity. So extremely has very, very high resolution. Should be 36. Accuracy is horrible. Precision is very good as well. Precision is very good. Accuracy is horrible. Sensitivity is also very good. Excellent. Was this a direct or indirect measurement? Indirect measurement for sure for the tire pressure gauge, just like we've done in class. Bias or precision error that can occur. Precision error, I mean, it shows here. Bias error that occurred, I mean, again, depending on your tire pressure gauge, if there's, it could be some calibration error in the spring. Is it digital? Is it not? Analog, et cetera, et cetera. So it could be a measurement error if it's an analog one as well. All right. Working with a new mystery material. Green viscous has amazing viscoelastic properties. Name is flubber. Let's calculate some of these values. So I'm going to go and I'm going to grab a quick. Where is being bending? I need to find. Where's my exam 1? Where is exam 1? I need to find just very quickly. Hopefully it's here. Oh, that would have been helpful for the problem set that I worked on previously. Not that one. Let's see here. Let's see if I have. To prep. I don't have an exam 1 prep notebook here. Exam 2 prep. I have lots of beam bending. I don't have a lot of exam 1 prep. I want to find my lecture notes. Oh. I can tell you what, I'm just going to write it out by hand. All right, let's do this. So first I'm going to quit all the evaluation here. So we have our z function, or what do we call it? Yeah, z function. Actually, I'm just call it PDF is equal to 1 divided by square root of 2 pi exponential minus z squared divided by 2. And I'm going to just prove that by integrate PDF from z from minus infinity to infinity. Great, that'll work. And now my z function is going to be x underscore mu underscore sig underscore, set equal to x minus mu divided by sig. All right, so I have some amazing activity, population mean of 10 milliseconds, standard deviation of 7. What percent of the data will exhibit a relaxation time greater than 17 milliseconds? So I need to integrate my PDF from a z value, z function of 17. Our mu is 10, and our standard deviation is this, greater than, so I'm looking at infinity. Multiply by 100, and that will be the percentage value. Excellent. What about the next one? How about less than 9? So if I go from 9, and I need to go from minus infinity to 9, that'll be that value. Next one, greater than 9. Let's say. So I'm just going to go from 9 to positive infinity. Good. What else? 10 and 17. Or 10 and 16, excuse me. 10 and 16. So 10 and 16 here. Again, all these multiplied by 100 again for percentages. What about between 8 and 17? Voila. Fantastic. Calculate the confidence intervals for the relaxation frequencies. So if I want to, so for example, integrate, I need that PDF from z from minus x to x, and I need to solve. So for what value that's going to occur at for 0.45. So that would be the z value, and then I'd have to actually then do a second step where my z function of x was it 10 and 7, set that equal to this. And then I need to solve. And then I do the same thing here, but for minus now. So those would be my bounds. So if I'm looking at 76, I'm just going to copy it right into here. Should be getting a little bit larger, which makes sense. Good. What about for 83? You get the picture. 95 will be 1.96. There are certain values it's good to remember. Be very impressive in a job interview, especially if you have a 95% confidence interval. 1.96, just like we predicted. Oops. And this is going to look really weird because it's going to be... Why does it have to freeze at this moment? Oops. Don't say it. And it failed, but you get the picture. All right, so we'll see you all in the next video. Thanks. Bye.